Hello, my name is Matthew Anderson, and this is my lab Faraday breaking for Physics 2. So the purpose of this lab is to demonstrate Faraday's law by dropping a dipole bar magnet through a metal loop of aluminum foil and to compare the results of the experiment with the computational model in Phys script for the time for it to fall through the roll. As a preview of the results, the experimental time was 2.0 seconds and the model time was 0.449 seconds. So the main physics principles in this are the Biot-Savart law for dipoles to calculate the magnetic field of a dipole anywhere in space, Faraday's law to calculate the EMF created on a loop by moving a dipole in space, the dipole force on a loop, Ohm's law to calculate the current from potential difference in resistance, and Newton's second law to calculate gravitational force, and Newton's third law to calculate the reciprocal force. So here we see the mass and dipole moment magnitude of the magnet and the dimensions of the tube. So the procedure is hold the tube, drop the magnet through the tube, and time how long it takes for it to reach the bottom, and then create a glow script model to calculate the model. So we assume that the magnet moves straight down, not side to side, that there's no air resistance, and that only magnetic force and gravitational force are acting on it. We assume the aluminum foil tube is made out of rings like a solenoid, and the system is the magnet in the tube, the surroundings is everything else. So here we have the code. We start by defining constant measurements and initial conditions. Then we define two functions. The first one is to create the first one is to calculate the magnetic field from a dipole at any point in space. The second one is to calculate the time derivative of flux, which is the EMF in a ring. And we create a loop here, which doesn't stop until the magnet has exited the bottom of the loop of the tube. In our model, we calculate a gravitational force and a magnetic force on the magnet due to every ring in the tube. And we calculate the net force and update the velocity and position of the magnet and print the results. And you can see that here. So for the what if the resistivity of the conductor were reduced as close to zero as possible? Well, the magnetic force would increase and the magnet would fall slower, and the current would increase due to Ohm's law. And what if we were to cut holes or slots into the tube? How would this affect the ring currents in your model? Well, there would be fewer loops, so the magnetic force would decrease and the magnet would fall faster. So overall, the time to fall in the computational model was much shorter than the experimental time, likely due to the assumptions that were made. The aluminum tube, it's not made of loops and rings, it's not a true solenoid, and there's other forces, and it's just not as pure as the model. So overall, Faraday's law is still successfully demonstrated in this experiment by visual magnetic Faraday breaking. And that's all I have.